Hello, here's our last video for Chapter 4, 2.4, Chemical Formulas. As always, here are the learning objectives for this section. Please take a moment to jot those down. So we're going to start by talking for a minute about a molecular formula and what a molecular formula tells us or represents. So it basically consists of two things, or tells us two important pieces of information. It tells us what atoms are present and how many of each. So for example, the molecular formula for H2O tells me that this molecule contains hydrogen and oxygen, and more specifically, it contains 2 atoms of hydrogen for every 1 atom of oxygen. So those are the two important pieces of information that we take from looking at a molecular formula. Now, in addition to molecular formulas, we have structural formulas, which tell us the same information, but just show how the atoms are connected. So here's a diagram with some information. So A would be our molecular formula, and in this particular case, we see that we have carbon and hydrogen atoms present, and again, more specifically, 1 carbon atom and 4 hydrogens. This would be our structural formula, B. So we see the 1 carbon and the 4 hydrogens, but the difference here is we also see how they are connected. These other two examples we'll talk more about when we get to molecular formulas with regards to Lewis structures and molecular geometries. So I would like to add a new word to your vocabulary here, and that word is Hofbrinkel. This represents all those atoms that exist as molecules. So many elements exist as discrete individual atoms. So let's say if I had, just pick a metal or something out of the periodic table, silver. If I was dealing with silver, it would just be the symbol of the element, and I would just be talking about an atom of silver. But these elements that make up Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, do not exist as individual atoms. They exist as molecules. And so anytime I have one of these elements, I need to also include a subscript 2. So I never just have hydrogen by itself. It would always be H2 and O2 and F2 and so on. You need to remember these, especially later in the year when we get it talking about chemical reactions and balancing chemical reactions. We need to make sure we always remember Hofbrinkel. When I have one of these elements, by itself, I must include that subscript 2. Another distinction that I want to make now with regards to formula are the difference between an empirical formula and a molecular formula. Now, later in this year, we will calculate and determine how to find these values, but for now, you should just know these relationships. An empirical formula is the simplest whole number ratio of atoms in a compound, whereas a molecular formula is the actual number. So if I take a look at these two examples here, you have an empirical formula of CH. That's the simplest ratio in which carbon and hydrogen can come together, but the actual formula for benzene, the molecular formula, is C6H6. You can see the ratios here stay the same. It's a 1-to-1 ratio still. Same idea here, that I have an empirical formula of CH2O, but if I multiplied each of these atoms by 2, I would get a molecular formula of C2H4O2. Again, you can see how those ratios of the atoms stay the same. It's just the empirical is the simplest way in which those particular atoms can group together, and the molecular formula is an actual. As I said a moment ago, we will learn how to calculate and determine these empirical molecular formulas later in the course. For now, though, you should understand those ratios and be able to identify what may be an empirical formula of some molecular formula and vice versa. Okay, last thing regarding formulas now in this section is the concept of isomers. So we will see this again later when we do Lewis structures of molecules, but just for now, understand the definition. So same chemical formula, but different structures. So the example the textbook gives you is C2H4O2. And you can have two different structures with the same molecular formula there, with the same combinations of carbons, hydrogens, and oxygens. So one way you could put those atoms together is a structure that looks like this. Two carbons, two oxygens, four hydrogens. And you could also have a structure that looks like this. Okay, so you can see in both cases I have the same number of carbons, hydrogens, and oxygens, but you can see that they're grouped very differently and therefore are two very different molecules that have different properties and behave differently as well. Like I said, later when we really get to drawing Lewis structures like what you see here, we'll talk some more about identifying possible isomers. Okay, the last thing to cover in this unit is a big one for us. It is the mole. Now, the mole is a very important unit for us in chemistry. It is a counting unit similar to a dozen. If somebody asked you how many was a dozen, we all know that's 12. The mole is very similar in that nature, in that 1 mole equals 6.022 times 10 to the 23rd of something. Okay, and you may recall that that value is Avogadro's number. Avogadro's number. So if I'm talking about a mole of something, whether that's a mole of atoms or a mole of marbles, I'm talking about 6.022 times 10 to the 23rd of them. Okay? The mole also helps to bridge the gap between units that we're familiar with, like grams, and atoms, ions, and molecules. And I always talk about this with regards to what I refer to as a little roadmap. So in the middle, we have this important concept for us in chemistry, the mole. So we have this city, the mole here. And out here we have unit grams. We'll call that a small town out there on the perimeter. And there's one road that connects grams to moles, but it's a toll road. So in order to travel on that road, you need the molar mass. You can see here I've provided a definition for the molar mass. Is the mass in grams of 1 mole of that substance, property expressed in units grams per mole. Now at this point in time, we're going to give you the molar mass. Later in the course, we'll talk about how to calculate that value. But at this point in time, you'll either be given individual atoms where I can just take the atomic mass from the periodic table, or if it's a compound or molecule, the molar mass will be given. Okay. We also have another town over here known as particles. And again, there's one road that connects mole and particles. And again, this is a toll road. So in order to get back and forth on this road, I need Avogadro's number. Okay. So in both of these examples, these values that I've put on these toll roads here equal 1 mole. So 1 mole equals the molar mass in grams, and 1 mole equals Avogadro's number of particles. Now, be a little more specific than just saying particles. So individual problems, like we'll talk about atoms, ions, molecules, formula units, So all of these units would fall under this category of particles. So as we work problems in chemistry and mole conversions here, this roadmap can come in very handy as you're learning this process because as always in chemistry, we want to think about when I read a word problem, what is the problem asking for and what is the problem giving me? So there is a very clear path to follow here when I look at this roadmap. If the problem has given me grams, and I'm out here, if it's asking for moles, then it's a one-step conversion, and I need the molar mass to do that. If it were asking for atoms or molecules, then it's a two-step conversion because you see there's no back road here that connects particles and grams. I have to go through the mole. So that would be a two-step conversion to use the molar mass to convert to moles and then Avogadro's number to convert to particles. Let's look at some examples so you can see what I'm talking about. So in this first one, a liter of air contains 9.2 times 10 to the 4th moles of argon. What is the mass of argon in a liter of air? Okay, so again, what is the problem asking for? Mass of argon. So it's asking for grams and it's giving me moles. So if I think back to my roadmap here, I'm starting out here. I'm actually starting right in the middle with moles. And I need to go to grams. So that's a one-step conversion, and I'm going to need to use the molar mass. In this case, it's argon, so I would just use the atomic mass of argon from the periodic table. So get in the habit of taking the number the problem has given us, starting there, setting up our conversion factor, units opposite so they cancel, and now I'm thinking about what unit do I know is equal to mole that I can go from? So think about mole again. In the middle of that roadmap is the city. I know I can go from moles to grams in one step. So 1 mole equals the atomic mass of argon. As I look it up on the periodic table, I see that the atomic mass of argon is 39.95 grams. So quick math here, moles cancel out, multiply, and I would get an answer of 0.037 grams of argon. Okay, pretty straightforward. Now let's take a look at this next one, a little more complicated. Gives me some information about saccharin, and it tells me the molar mass. As I said, at this point in time, we're not going to ask you to calculate molar mass. We'll get to that later. So if it's a molecule like the one given here, I would have to give you the molar mass so that you can do the conversion. Okay. So we're starting with 40 milligrams now. So this problem throws in a little wrinkle in that we talked about how grams and moles are equal. So if I get a situation like this, before I can get to my roadmap, I'm like even further out of town now. Before I can get to that town of grams, I have to do a little conversion, a little metric conversion here to go from milligrams to grams. Okay, we know 1 gram is 1,000 milligrams. Okay, so now I'm at grams, and there's only one place for me to go from there, which is to the mole. So again, grams per mole is that molar mass. So it's given to me right here in the problem, 183.18 grams per 1 mole. You can see here that the units, grams, and moles are flipped as compared to our first example problem, and that's fine. Units opposite, so they cancel. So those can go either way depending on which way you're going on your roadmap. Okay, so now we have effectively canceled out milligrams and grams, and we're sitting at mole there. And this question is asking not for moles, but for molecules. So I have to take that final step and go from moles out to particles. And again, that's using Avogadro's number and the specific particle here. We're talking about molecules. So I'll go ahead and use the term molecules as opposed to particles. Okay, so do that math there, and we see we get a value of 1.31 times 10 to the 20 molecules of saccharin. Okay, now this problem gives us an extra step to consider as well. In addition to asking how many molecules of saccharin, it also asks us how many carbon atoms. How many carbon atoms? Okay, so that's not a big deal because that just requires one additional step. And actually, I'm going to show this. If the problem had initially, and this is one place you need to be careful, if the problem had initially asked for carbon atoms, I would have done everything the same that I've done here. I just would have taken one more step, and that step would have been in 1 molecule of saccharin. I have, if I look at my molecular formula, my formula here, I have 7 atoms of carbon. Okay, so you can see here I could have stopped at molecules if the problem was asking for molecules, but if it was asking more specifically for atoms of carbon, then I need to take that additional step given the formula here. And I would have found this to be 9.17 times 10 to the 20 carbon atoms. Okay, so I will just say be careful. As always, what is this problem asking for? Sometimes we're dealing with atoms, and so using Avogadro's number gets you to atoms. But in this case, I'm dealing with a molecule, so I'm dealing with a group of different atoms. So using Avogadro's number gets me to that whole value. In this case, that whole saccharin. If I wanted atoms, I would need to then break out the atoms individually, like I did here with carbon. Okay. That wraps up the last section of chapter 2. Thank you and good luck.